So these are the sections of the paper. This is where we're going. Today we're doing basic neurophysiology in 2 lectures just to revisit the electrophysiology. We'll then get into some developmental neuroscience next week. And in the weeks after that, we'll go into some progressively cognitive neuroscience. We'll start out talking about how neurons process information. We'll go on to how neurons talk to each other. And we'll build that up progressively into bigger and bigger systems of neurons and neurological pathways until we get, hopefully, some understanding of the higher processes like sleep and memory and awareness and so on. So today then, I'm going to talk to you about membrane potentials. And we'll start off with where it all starts off. This is the sodium-potassium ATPase enzyme, sometimes referred to as the sodium-potassium pump, which is embedded in the cell membrane of all tissues. So what we have here is an enzyme at the top, E1, which is phosphorylated by the degradation of ATP to ADP, a standard energy-dependent process, and which binds with sodium ions and takes the sodium ions across the cell membrane. Once it gets across the cell membrane, it meets up with 2 potassium ions, dephosphorylates, and takes the potassium ions back. You can see from this that the conformational change is progressively opening the binding sites to the intracellular and the extracellular environment, and the affinity for the different ions is changing as the conformation changes. So that when it's exposed to the intracellular environment, it has an increased affinity for potassium ions, and then when it's exposed to the extracellular environment, it has an increased affinity for sodium ions. And so it's that changing affinity and the changing conformation that's driven by this energy-dependent process that sets up the membrane potential. The second part of the membrane potential we need to consider is the potassium channel. So what we're getting here is the potassium is free to diffuse back out of the cell following its concentration gradient, but because those are all positively charged ions, that's obviously imposing a charge differential onto the cell membrane, and that charge differential is inhibiting the process of diffusion. And so when the cell is at rest for an excitable tissue or for any other tissue in the body under normal circumstances of equilibrium, we've got a tension both of the extracellular and intracellular concentration of ions and also the relative charge on the intracellular and the extracellular side of the membrane. And that's why the main extracellular anion is sodium and the main intracellular anion is potassium. It's also why we get this membrane potential or charge change across all of the cells of the body. And when we look at action potentials, then the action potentials are changes in that membrane potential which the excitable tissues have developed the ability to achieve in order to transfer information. Now, in this paper, I'm not going to expect you to derive either the Goldman equation or the Nernst equation, because it takes me a long time to do that with a book open in front of me. But I might ask you to reproduce either the Goldman or the Nernst equation, and I might ask you to explain the different parts of it and what the different parts of it mean in terms of the membrane potential. So let's go through and have a look. Vm at this end is the membrane potential, usually expressed in millivolts. And the first part of the equation is a set of constants. R is the universal gas constant. T is the absolute temperature. And F is the Faraday constant. And again, it's possible to explain why all of those constants are in there and to derive all of those constants, but the maths is both horrendous and pretty much unnecessary. This is the business end of the Goldman equation. And what we're looking at here is the relative concentration of the electrically active ions outside and inside the cell. So you can see that the first term we've got is the ratio of potassium ion concentration outside the cell to inside the cell. Then we've got sodium, and then we've got chloride. One thing to notice with chloride is that all of the positively charged ions are outside over inside. But because chloride is negatively charged, it's inside over outside. It just flips over. And we can express the Goldman equation in terms of all the positively and negatively charged ions that contribute to the membrane potential. We normally only consider these three because these are the big three. But after that, we've got the negatively charged proteins, the organic anions. We've got the, let me think, what's next? Calcium is next. Magnesium, again, I can't really say important because they're a very minimal contribution. But we can go through all the ions that exist in the body and add them onto the Goldman equation, making progressively lesser and lesser contribution to the membrane potential. Normally speaking, we just express the main three and we put some dots on to indicate that all the other ions could be there if we wanted them to be. The Nernst equation is a special case of the Goldman equation. So you can see that the Nernst equation down here is almost the same as the Goldman equation. But what we've done is we've taken away all the other ions apart from sodium and not considered them. And the reason that the Nernst equation is useful is that sodium ions are not the only ions that change during action potentials, but they're the major ions that change during action potentials. And so if we just look at changes in concentration of sodium over the membrane, often during an action potential, we can get a good approximation of the changes in membrane potential. And in fact, the reason for that is because under normal circumstances, sodium is by far the least permeable of the ions through the cell membrane. The cell membrane has an effective block on free permeability of sodium ions. Potassium ions, as we saw in the video segment, have very free permeability, a permeability of about 50 times that of the sodium ion. Has a much higher permeability, about 10 times that of sodium. It's not up to potassium, but it's still very permeable. And so under normal circumstances, the sodium ion controls the resting membrane potential and the action potential. And the other ions are kind of also-rans. And we can see in different cells that different permeabilities to the sodium ion can give us very different resting membrane potentials. And those resting membrane potentials affect the function. And the reason they do that is because the equilibrium potential for the three different ions is very different. The equilibrium potential for the potassium ion is minus 90 millivolts. We've got a very permeable membrane to potassium under resting circumstances, and so we have a membrane potential that's close to the equilibrium potential for potassium. Chloride is in a similar place, but the equilibrium potential for sodium is in a very different place. It's plus 55 millivolts. And so when we have an action potential going through and the membrane becomes more permeable to sodium, then we have a great change in the membrane potential. The membrane potential becomes much more positive. So let's look at some different tissues and look at how the permeability to sodium affects both the membrane potential and the cell function. Striated muscle, first of all. Under normal circumstances and resting, striated muscle is very impermeable to sodium. or rather the sarcolemma, the cell membrane, is very impermeable to sodium. And so the resting membrane potential is very close to the equilibrium potential because of that lack of permeability. So the sodium is having almost no effect on that membrane potential under resting circumstances. When we get to threshold, which is the point at which cells begin to undergo an action potential, we'll see that for most tissues that's around about minus 55, minus 50 millivolts. And so striated muscle sits a long way below its threshold under normal circumstances. And that means that it's very, very unlikely to undergo spontaneous depolarization and therefore spontaneous muscle contraction. So your striated muscle is very, very unlikely to spontaneously undergo a contraction without an action potential arriving from a nerve because it has this very stable resting membrane potential. If we compare that with smooth muscle, under resting circumstances, smooth muscle is more permeable to sodium. And that means that the membrane potential is dragged more towards the sodium equilibrium potential than it is in striated muscle. The membrane potential resting sits around about 50 millivolts, and that means that smooth muscle sits at around about or just above its threshold potential. And that means that smooth muscle can contract spontaneously much more easily than striated muscle. And so now we've built an electrophysiological model that allows us to understand the differences in function between these two tissues. Striated muscle sits and does nothing unless it hears about it from a nerve, and then it contracts obediently. But smooth muscle works much more as an active functional tissue that's contracting a bit and has a tone most of the time. And sure, activity from nerves can influence and alter the behavior of the smooth muscle, but it's more of a control of a system that's ongoing. So we've got two different tissues, two different permeabilities to sodium, two different resting membrane potentials, and those give us two different functions in those tissues. If you look at the action potential for cardiac muscle, in the resting phase, you'll see that we've got this permeability which is causing that membrane potential to change over time during the resting phase. So in the refractory period, this cardiac muscle is sitting almost down where striated muscle is. It's very, very unlikely to undergo a contraction. But as time goes by, that permeability to sodium alters the resting membrane potential until it reaches threshold, and then we get another action potential. And the permeability to sodium is what's changed by the autonomic innervation of the sympathetic and parasympathetic nervous systems, so that the sympathetic system makes this membrane more leaky to sodium so that it gets to threshold more quickly and increases heart rate. The parasympathetic system makes it less leaky to sodium so that it gets to its threshold more slowly and reduces heart rate. Again, a different tissue, a different way of handling sodium permeability that's related to the function of that tissue. If we have a cell membrane sitting here with its normal membrane potential, and we stimulate it with electrical stimuli that either make the membrane potential for a short period of time more negative or less negative, you can see that we have a system with negative feedback where it responds to the external stimuli, but then it tends back to its resting state. And the bigger the stimulus, the more it deviates from its resting state, but it tends to return to its resting state. Until we give a stimulus that takes the resting state to a point that we call threshold. And at that point, something changes in the membrane. And that change in the membrane causes the membrane not to return to its resting state, but to change its permeability to sodium completely, such that the membrane potential becomes close to the sodium equilibrium and not the potassium equilibrium. And we call that an action potential. And under normal circumstances, an action potential will get to around about plus 10 or 15 millivolts before it turns around and comes back to its resting potential. So what's happening? How is that action potential being generated? What's the change in the membrane that's altering that permeability to sodium? There are two main populations of sodium channels, and in those two populations there are loads and loads of different subpopulations that we might get onto later on in the course, but for the moment we're just going to think of two different sorts. And the sodium channel that is responsible for this change beyond threshold that generates the action potential is called the voltage-gated sodium channel. It's a sodium channel that opens when the cell membrane reaches threshold. The change in potential difference across the membrane causes a conformational change in the sodium channel, causes the channel to open. It's a voltage-gated sodium channel. The other sodium channels that we'll meet later on are the chemically gated sodium channels. We'll meet those in the next lecture. The chemically gated sodium channels are receptors, and so a molecule or a ligand will attach to that receptor and that will cause a change in conformation. But these voltage-gated channels don't need any molecules, they just need a change in the membrane potential to undergo the change. If we look at the action potential, the foot and the rising phase and the peak are all about the increase in the action potential. And then there's an overshoot and a falling phase, and around here we've got a little bit of negative feedback that the membrane undergoes until it settles back down to its membrane potential. So it kind of comes back down, but it's coming back down so quickly that it has to hunt a couple of times to get back to its membrane potential. It doesn't go straight back there. And the action potential is about the movement of sodium ions through the membrane, but also the movement of potassium ions through the membrane. Remember that the membrane is usually permeable to potassium ions. But normally the potassium ions diffuse into the cell because of the negative membrane potential within the cell, dragging those potassium ions in. What happens to the potassium ions when the cell goes positive? Are they still going to be diffusing into the cell? No, they're going to start diffusing out of the cell. That positive voltage is going to drive them out of the cell. So what we see when we look at the ion movement in an action potential is an initial movement of sodium ions into the cell through those voltage-gated channels, and a slightly later movement of potassium ions in the opposite direction because the membrane is usually permeable to them anyway. And so here we've got those two processes represented at the bottom. The ionic conductances of the sodium movement and the potassium movement. And you can see here that those two processes, this giving us a positive change and this one giving us a negative change, when they combine together, they give us this thing that looks like the action potential. So it's a switch over of ions, it's a movement of the two ions across the membrane. And the nice thing about it being this switch over of the two ions is that the action potential is very, very localized to the area of the cell membrane that's undergoing that change. It's not a big thing through all the tissues, it's a very localized event. And that means that this change in voltage can occur with very little change in energy. It's, relatively speaking, few ions that actually have to move across the cell membrane to produce this action potential. In fact, it's a tiny fraction of the ions in the intracellular and extracellular fluid that move across. And that means that this is a very energy-efficient process. We can get this change in voltage, which is quite dramatic, with the movement of relatively few sodium ions across the membrane, And then after the action potential has gone, the sodium-potassium ATPase can quite quickly mop up the imbalance and sort things out so that the membrane concentrations and the resting membrane potential are back to normal very quickly. And the whole thing is over in 3 or 4 milliseconds. It's a very rapid change. So what use is this change in electrical activity at one point in the membrane? And the answer is, at one point in the membrane, it wouldn't really be very much use at all. But the nice thing is, because these sodium channels are voltage gated or electrically gated, once we get this change at this point in the membrane to such a positive membrane potential, that will drag the adjacent areas of membrane to their threshold, and then they will undergo this conformational change, their ion channels will open, and they will undergo an action potential. So if we electrically stimulate, for the moment, a point on an axon of a neuron, the action potential will spread in both directions along the axon, because the change in electrical potential at the point we stimulate will drag adjacent areas to their threshold. They'll undergo an action potential, and they will drag the next areas along to their threshold, and so it will go on. So here you can see we're effectively getting not a straight in-out movement, but a kind of a circular movement, a progressive twisting of ions along the cell membrane as the action potential moves along the membrane. That's useful because it enables us to record what's going on as a far field, and I'll spend a few minutes talking about far fields in just a second. But it's also useful because it gives us that concept of moving electrical change, which is the basis of the function of the neuron, or rather, the basis of the electrical function of the neuron. So what affects this movement along the axon? Well, we can model axons with a mess of resistors and capacitors and resistors inside. So here we've got the resistance of the plasma membrane across the top and along the bottom, and the internal resistance of the axoplasm and the internal capacitance of the axoplasm. And if we model the axon like this and we apply, here's a battery, a potential difference at this point, we can model the rate at which the action potential moves along the axon. If we get the resistances and the capacitances right, we get the same kind of rate of propagation of an action potential in this circuit as we get in the axon. Before we talk about what that rate might be and how useful to us as animals that might be, let's just talk a little bit about measuring action potentials and how we measure them. And to do that, we need to talk about far fields. Has everybody met the ECG? Yeah? The concept of the electrical activity of the heart that you can measure by attaching electrodes to your wrist or your hand and your ankle, and you can get that electrical change that occurs when the heart depolarizes. That's a far field. And what we mean by that is that the electrical change that we see in the heart is propagated through the tissues as a number of areas of iso potential difference. So here's a heart beating here. And let's imagine that at some point in the cardiac cycle, the heart is positive here and negative here. We get electricity moving through the heart, but we also get these far field potential differences conducting out through the conducting tissues of the body. And if we place an electrode here and an electrode here and measure the potential difference between them, we will find that this electrode is positive, reflecting this point in the electrical field, and this electrode is negative, reflecting this point in the field. And that's how we record the ECG. It's not about sticking electrodes onto the heart to record the electrical activity. It's about recording this radiation of potential difference through the body. And we call that radiation a far field, because it's not being recorded close to its site of propagation, it's being recorded far from it. If we were recording actually from the heart, we would call that a near-field recording, because we're recording near to the site of propagation. Every electrical change in the body has this far field. And the far field that we get when we record is a summation of all of the activity. So if you have the opportunity to record an ECG and you're relaxed, that's fine. But if you start to contract one of the muscles in one of the arms that has the electrode attached to it, you'll find that there's a lot of interference to the ECG, because you're now recording far fields from the heart and also far fields from this muscle in your arm that's contracting. So everything adds together to give you a complete far field. And the far fields get weaker and weaker the more they spread out from the site of origin. The ECG is conveniently the biggest far field generator in the body at rest. And so it's really easy to measure an ECG from electrode sites that are really quite distant to the heart. But it's possible to measure the far field of an action potential. We just need to get the electrodes closer to the nerve axon while we're recording, because the far field is much smaller. And we also need to find a way to get rid of some of the other activity like the ECG, which will cause noise in our recording. This is a near-field recording of an action potential. We've actually stuck one of the electrodes into the axon. And so we're recording from near to the site of propagation of the electrical change. And the other electrode is some distance along the axon. As the action potential moves, we're recording the potential difference of this electrode compared to the potential difference of this electrode. So let's imagine that the axon generates an action potential which goes in this direction. You can see that as the action potential moves towards both electrodes are about equally positive. They're both seeing the positive side of the action potential. As it moves between the electrodes, now this electrode is seeing the positive end of the action potential, and this electrode is seeing the negative end. So we're seeing a big action potential. And then as it moves past this electrode, we're coming to a point where both electrodes are seeing the same negative, the same thing. So we're getting no recording, no difference in potential difference, a big recording, and then no recording again. And that's why an action potential that is really quite straightforward can look quite complicated. Here the action potential is approaching the first electrode, here it's approaching the second electrode, and here it's kind of waning as the action potential moves on. If you want to make things simpler than that, you can crush this area of axon just before this electrode so that you damage it and the action potential won't travel beyond it. So if you do that preparation with this crushed region, the action potential stops before it passes the second electrode. And that gives us a much more straightforward and simple action potential that's just rushing up to the second electrode and then stopping. We normally record with two far-field electrodes. We don't normally put either of those electrodes into the axon. We've normally got two electrodes which are distant from the axon, although often quite close, and we're recording far fields. And in that situation, we're starting to record the vectors from this circular activity in the cell membrane as the cell membrane moves along, as the action potential moves along the axon. So even with a crushed region, because of those changes in the direction of the far field, we see a much more complicated action potential. And so the action potential that you see when you're doing standard physiological recording is usually at least triphasic. It goes down and then up and then down again. And that's because of the complexities of recording with two far-field electrodes and recording this complex ion movement as it moves along the axon. So it's a relatively complicated thing to record. What factors affect the rate of action potential propagation? There are many. These are the three main ones. temperature. As the temperature goes down, so the rate of action potential propagation also goes down because of changes in the fluidity of the cell membrane, which affect its ability to allow those proteins to undergo conformational changes. And as you'll be aware, the rate of any enzymic reaction reduces as temperature drops. Yeah, you remember that classic halving of enzymic rate that you get with a drop of 10 degrees C? You guys done that experiment at school or wherever, where you get some sort of gastric enzyme and you digest some sort of protein in a pot, and then you look at how much has been digested, and you see that if the pot's at 30 degrees C, you get this rate of action, and if the pot's at 20 degrees C, you get half the rate, and if it's at 10 degrees C, you get a quarter of the original rate. You get a drop in rate of a half for every drop in 10 degrees C. And we tend to think about that for digestive proteins and proteins we can get to, but it's the same for all the other proteins as well. So most of the metabolic processes of the body will drop dramatically with temperature. The diameter of the nerve fibre affects the resistance of the nerve fibre. And so as diameter goes down, we get a reduction in action potential propagation rate. And in fact, if we look at unmyelinated fibres within the human body, we tend to see a typical rate of propagation of around about half a metre a second, or thereabouts. So, for example, your pain pathways are unmyelinated C fibres. And if I drop a brick on your foot, you'll feel that straight away, but it won't become painful for about half a metre a second, 2 seconds. Yeah? You'll drop the brick on your foot, you'll go, ooh, ow! It's a couple of seconds later that the pain really kicks in, because the pain is carried in unmyelinated narrow fibres that have a slow rate of conduction of action potentials, and it takes a while for that information to get to the brain. So if we've got a slow rate of conduction in these unmyelinated fibres, what's the difference with the fibres that tell us that a brick's just dropped on our foot, the touch fibres and the A fibre fast pain fibres? What have those fibres got that the C fibres haven't got that increase the rate of action potential propagation?
Nodes of Ranvier?
Yep, nodes of Ranvier, that's right, they're myelinated. Okay? The myelination, and particularly the gaps between the myelination at the nodes of Ranvier, magically it seems almost, increase action potential propagation rates by 2 orders of magnitude. So that the fastest myelinated fibres in the body don't have a rate of action potential propagation of about half a metre a second. They can have rates which are up as high as 120 metres a second, which is much more like it if you want to exist in an environment and work out what's going on while it's still important. This is a diagram of a typical textbook neuron, which I ripped off from a typical textbook. And you can see that the myelin sheaths wrap around the axon, but they have little gaps between them called nodes of Ranvier. Myelin is effectively cell membrane. If we look at a section through a node of Ranvier, actually, yeah, we'll come back to that. If we look at a section through a node of Ranvier, you can see all these stripy processes here, which are invaginations of the cell membrane of the Schwann cell, which is the cell that makes the myelin sheath. And those fatty invaginations are what we know as myelin. It's a fatty substance, and therefore it's an insulator. It doesn't conduct electricity. And it's the exact equivalent of insulating a small electric cable with a plastic insulator. It's preventing this area of the axonal membrane from electrically contacting the extracellular fluid. And if you look at a typical nerve fibre, you can see that the axons, which here are stained in this mucky sort of greeny brown colour, are trapped inside or housed inside these myelin sheaths. And if you look down the side at the myelin sheaths, you can see the nodes of Ranvier. There's one just here, another one just here, where there are small gaps between those myelin sheaths. That has two effects. That it means that the areas in the node of Ranvier are the only areas that are electrically in contact with the external extracellular fluid. And so these are the only areas that can undergo action potential generation. And so instead of the far fields from this bit of axon influencing the next bit and the next bit and the next bit and giving us this action potential that goes slowly along, the far fields from this bit of axon influence this next bit of axon, and the action potential jumps along to the next node of Ranvier. The areas between the nodes of Ranvier here don't undergo action potential. The action potential jumps, and we call that saltatory conduction. It's a kind of a jumping conduction. That means that the action potential propagation is much faster in a myelinated fibre than an unmyelinated fibre because it jumps from node of Ranvier to node of Ranvier. But it has another advantage for the axon as well, in that because these areas don't undergo action potential generation, they don't need any electrically gated sodium channels. And so the sodium channels and the proteins in this cell membrane migrate to the nodes of Ranvier. And under normal circumstances, those are the only bits of the axon that have high concentrations of those proteins. That means that there are fewer proteins that the axon's got to make. It also means that there are fewer ions moving across the axon, so we don't need as many sodium-potassium ATPases. We don't need as much metabolic energy to maintain the membrane potential. So it's a double whammy, really. We get an increased rate of action potential propagation, and we get it for less metabolic overhead. Everybody wins. If we look at the compound action potential, what we've got here is an action potential recorded in a mixed nerve following stimulation of the nerve at a distant site. So we might be stimulating at the wrist and recording at the shoulder, or similar. And therefore, as the milliseconds pass in this recording, we are recording action potentials going by the electrodes from progressively slower and slower conducting axons. So the fastest axons in the body are the A fibres, and we divide them into three populations, A alpha, A beta, and A gamma. The B fibres sit in the middle, and the C fibres are kind of also-rans that come along at the end. But those different fibres have different functions relating to their need for speed, as it was. Acute pain doesn't need to be that fast because you already know that your foot's been hit by a brick because you've got the touch and the fast pain, the A fibre pain. And so this is really just the acute pain that stops you using that foot again for some little time. Doesn't have to be there instantaneously. The A alpha fibres and the A beta fibres are the fibres that are associated with fast reflex feedback. Specifically things like muscle spindles and Golgi tendon organs, where the information that you're getting from the tension in the muscle only relates to a short period in time. And you've got to get that information back to the central nervous system and processed in a reasonable time frame so that the body can adjust itself to what's going on in space. So there we need these fast fibres. And so we see different rates of propagation of action potentials in different nerve fibres, again suited to their function, and that's what gives us the compound action potential. So that's a quick review of membrane potentials and action potentials with a little bit about how they relate to the tissues and the functions. What we're going to look at next time is what happens at the end of the neurons, what happens at synapses, and how do neurons communicate with each other.